I hope everybody can see the screen. However, I'm not going to start here. I'm going to go to a much earlier page. Oh Lord, where was it? Later page, actually. Let's go there. Oh, wait a minute. No, it's page 454. Yeah, it's I'm having trouble with mine. Oh, these are two different representations of the book. So if, yeah, all right, I'm already on the page that I want to be on. This is 454 in the class notes as opposed to 454 in the book. Okay, well, I promised to do this example and I postponed the homework until Friday. The homework that's due tonight at midnight, it's due now on Friday. So this is a simple problem, but I thought I'd do it anyway for you because the first three homework problems require the solution of this problem. So let's consider the torus T2 embedded in Euclidean 3 space. We can label it with coordinates like this. We have a cosine phi in which x and y rotate, and then we have another angle theta, which is where well, x, y, and z rotate. So let me see if I can write. Once again, there's this tricky business of I have to tap to connect the Apple Pencil, and I think I'll switch to blue. Okay, here we are. So let me draw you this torus. It essentially looks like this, and in there we have this, and we also, well, it looks kind of like that. So what is the phi, the angle phi? The angle phi is from basically the center of the torus out to a point here, and over there, this would be an angle phi, and the angle theta, on the other hand, is the angle from the, let us say, center of the torus to a certain point on the torus. That's the angle theta. So with as you rotate phi, you go all the way around the torus. As you rotate theta, you go around the torus this way. So it's an amusing kind of thing. It's simple, but it's this, by the way, topologists talk of this as a surface with one hole. And you can see where the hole is. It's the center of the donut, the part that you don't get to eat because there's nothing there. Now I see a stupid phone call coming through, and I'm going to just reject it. So what are the basis vectors? Well, by definition, if this is the point, the arbitrary point on the torus is a two-dimensional surface embedded in Euclidean 3 space, and the basis vectors, then the theta vector is the partial of p with respect to theta, and it points in all three directions, whereas the phi basis vector is the partial with respect to phi. And if you differentiate p carefully, you see you get these two expressions. I don't know why there's no, oh, I do know why there's no number sign here. I'm going to have to fix this. So let me say numbers. So the metric of the torus is just the dot product matrix of the dot, well, it's the dot product of the basis vectors. And so E theta dot E theta, you just dot this with itself, you get a sine squared there, you get cosine squared plus sine squared, and that's 1. And so this is altogether cosine squared plus sine, so it's altogether r squared simply. I see I screwed up here in the notation. E theta dot E phi is this, which is actually 0. This is so irritating. Why? I see. I just stupidly put that in there. So let me just fix that. And then E phi dot E phi is non-zero. And if you compute it, you get that. And putting them together as a matrix, we get the normal representation of the matrix, of the metric of a torus, represented as a matrix, and it's r squared, and then r plus, big R plus little r, sine squared theta. Big R is the distance from the center of the torus to the other center of the torus, which is a circle. Well, big R, let's see, I'll go back to blue. Big R goes from the center of the torus out to here, say, that's big R. And little r just goes from this center to there, that's little r. Well, I think you guys all understand that. The inverse of this metric is obviously just, since it's diagonal, it's just the diagonal of the inverses. All right, so that's the problem, and for all I know, you guys have already done this homework problem in anticipation of turning the homework in today. But as I said, the homework's been postponed till Friday. I thought I would do a new example, and this is on page 458, I think. By the way, we have a chat thing here, and this is formally the problems class, and so it's entirely appropriate to type in a problem or a question in the chat thing. If you use capital letters, I'm more likely to see it. But anyway, let me just say that. I'm a little puzzled. Okay, so what I wanted to do is I wanted to show you this extra bit here. And it was foreshadowed by the statement that the affine connection is not a tensor or transforms inhomogeneously. I thought I would derive that for you just from the basic definition of the tensor in terms of a dot product of a cotangent vector with the derivative of a tangent vector. And what you do is if you just go to the primed coordinates, then you have the primed cotangent vector and the prime tangent vector and its derivative with respect to the primed variables. And so this thing is a contravariant vector, so it transforms this way. This EI is a covariant vector, so it transforms this way. And this derivative, well, this is also a covariant vector, and it transforms this way. But what happens here is that this derivative hits that derivative. And then you get something that isn't part of a tensor. And so if you have this derivative just act on EM, and then you get this first term where the dot product hits this partial of EM with respect to EN, this one, and then the in other words, the partial, all right, let me just maybe dope this out just a bit here. What we have here is partial xn of partial xm partial x prime I of EM. And so this is two terms. One term is partial EM partial xn times partial xm partial x prime I. And then the other term is EM times the second partial of xm with respect to xn and x prime I. So this bit here is the part that's, so to speak, inhomogeneous. And so that's, in fact, this thing here that I separated out. And then we have the dot product of EP with EM, that's this. And then we have this term, and okay, so this is, so I've explained this second line. I've just changed the notation here to the common notation to, in order to get back to the definition of the Christoffel symbol of the second kind, or the affine connection, and it's the Libby-Civita affine connection. This is all standard relativity. And then EP dot EM, well, this is just delta PM, because the cotangent vectors are orthogonal to the tangent, orthonormal to the tangent vectors. And so we have that. And then putting them together, we get this inhomogeneous piece. Okay. So what we say here is that the Christoffel symbols are a connection, but not a tensor, because they transform inhomogeneously. In other words, there's an extra piece here. And that's the way all of these connections transform. And in particular, the electromagnetic field is a connection. It's not really a covariant vector. And the, well, it's a covariant vector in terms of coordinate transformations, but in electrodynamics, we have these gauge transformations, and it's not, whoops, what the hell happened? Oh my Lord, what is this? All right, hold on, I've got to, as usual, you touch the screen the wrong way and the world ends. Oh Lord, I can't find this thing anywhere. This is just, Bloomberg belongs over there. Let's just see if, no, it's not there. Let's see, is it here? No, it's not there. Is it here? No, it's not here. Did it go over here? No, oh Lord. All right. So what seems to have happened, oh, I see. What happened was my, the iPad thing, I touched the iPad the wrong way, and all right, so I have to move this back to there. Okay, so finally back to normal, or what passes for normal here. And let me get rid of this damn thing. And why there are so many things there, I don't know. Okay, so as I was trying to say, the electromagnetic field under a gauge transformation turns into an prime is an plus the derivative of some scalar, which we call lambda. And this foreshadows something that I want to talk about presently. You might say, well, here's this inhomogeneous term, and previously I said, it's this inhomogeneous. Well, these are two different, these are actually two equivalent homogeneous terms. They're just different inhomogeneous terms, and it's just different ways of writing them. You see, in this one, you have two prime derivatives here, and in this one, you have one prime derivative and one unprimed derivative. And if I'm not mistaken, in the book, let me just move this. Well, I get the other. Yes, there it is. Okay, so in the book, here, let me just show you. These two forms are equivalent. I assigned it as an exercise. I don't think it's worth going through now. They're just two different forms for this inhomogeneous term here. So I'm going to skip now to group theory. Once again, we used to teach various things in this department, and now we seem to focus so much on qubits that we no longer teach a second semester of general mathematics, and we also don't teach classical mechanics at all. So what I'm going to do then is skip to group theory and tell you some things about group theory. And so I'm going to, this is all in the book. So what is a group, first of all? This damn. Okay. So let's see, I've got this a little too small. Let me make it a little bit bigger. Well, that's about, all right, I'm going to have to shrink this a little bit. Okay, so what is a group? A group is a set of elements and an operation. The operation is called multiplication, but it could be addition. It's an abstract operation. And what characterizes a group is that the product, which again, it could be sum, it could be something else, but anyway, the operation F operation G is in the group, and so it's easier to think of it as multiplication. This is called closure. Moreover, F times GH is the same thing as FG times H. This is called associativity. So annoying. And then there's an identity element, E, in the group, such that G times E is equal to E times G is equal to G for any G in the group. And every G in the group has an inverse in the group, such that G times G inverse is equal to the identity E, and G inverse G is equal to the identity. So that's basically what a group is. And the essence, apparently, or at least almost all the examples I know of a group, well, let me not try to characterize things universally. I'm a physicist, not a mathematician. But what I can say is that transformations naturally form groups. One can think of, in particular, transformations that leave some property invariant naturally form a group. And I think I'll just leave it at that. One set of one kind of transformation is if you just change the order of a finite set of objects. In other words, you have an ordered set of objects, and then you change the order. That's called a permutation. And then in physics, we're very interested in groups of coordinate transformations. And then there are the linear transformations, just a translation is what this is called. And you just move everything in a given, displace every point by a given 3-vector. Then there are the transformations that are associated with special relativity in the name Lorentz and Minkowski. And I'm quite amazed at Lorentz. He was born before the Civil War. Wow. And he lived till way after the First World War. Wow. So that's quite a while. Anyway, Lorentz transformations leave this sum of the space, the squared distance from the spatial origin minus c squared times the time squared invariant. So these are called Lorentz transformations, and they leave. You can think instead of distances between two x minus y squared in the sense of this metric with a minus sign here. All linear transformations that leave that squared distance invariant, those are called Poincare transformations. They're translations and boosts and rotations and so forth. Now, in groups of translations, the order of multiplication doesn't matter. You can go east and then north, or you can go north and then east. And if you go the same distance in both cases, same distance east and the same distance north, you wind up in the same place, whether you go forward or whether you go east, north, or northeast. A group that in which the order of multiplication doesn't matter is said to be an abelian group, named after Niels Abel. I think the story is that he was fooling around with the wife of some mathematician who murdered him. But that may be totally apocryphal. I'm not an historian. I don't know. Anyway, poor Abel lived only to be 27 years old. So most groups, on the other hand, are non-abelian, which is to say that the commutator of two elements, GH minus HG, isn't zero. If it's zero, it's said to be abelian. If it's non-zero, it's said to be non-abelian. Now, matrices naturally form groups with multiplication defined as matrix multiplication, inverse as the inverse of the matrix, and so forth. And examples of this are the orthogonal groups that leave invariant x1 squared plus ... plus xn squared. That's the orthogonal group. If you say, well, you want the determinant of the transformation to be unity, then it's called SON. SO3 is ordinary rotations. O3 is ordinary rotations plus parity, where you can reflect XYZ into minus X minus Y minus Z. Then there are the unitary groups, which are like the orthogonal groups, but for complex numbers, and they leave this quadratic form invariant. And then there are these things that are that we don't talk about much in physics, but which I think are going to rear their head at some point. And they're sort of hidden in physics, but they're obviously important because, for example, the symplectic group can be thought of as a set of all 2n by 2n matrices that leave invariant the commutation relations of quantum mechanics. And that's called the symplectic group SP2n, if there are nq's and np's, are the symplectic group over the real numbers. The number of elements in a group is the order of the group. A finite group is a group with a finite number of elements. The parity group is a group of order 2, 1 minus 1. The phases e to the I 2k pi over n is a group of order n. It's called the cyclic group Zn. And then when we go to physics, what we have often are continuous groups, for example, the translations, the rotations, the Lorentz transformations, the Poincare transformations, and above all, the transformations of general relativity, which are general linear coordinate transformation, general coordinate transformations. In particular, the partial x prime I, partial x j, say, this is a 4x4 real, an arbitrary 4x4 real matrix, and these things form a group called GL, general linear group, 4 dimensions, real numbers. And so that's another group. Now, there are things called representations of groups, and namely, for each element of a group, one can associate a matrix, and you have a representation if the multiplication law of the group, namely f times g gives you fg, well, if the matrices respect that, so d of f times d of g is d of fg, then we say we have a representation of the group. And by the way, when I was a graduate student, this was very new in physics, and one of the young professors at Harvard was Sidney Coleman, and he had just done his PhD under Murray Gell-Mann at Caltech, and Gell-Mann was the person who brought group theory, at least the theory of unitary groups, into physics. And of course, Gell-Mann had done many things. Anyway, so Coleman really knew about representations of SU2 and SU3, and he would amaze other faculty members by the things that he could do with SU3. Okay, so one thing in particular here is that compact groups possess finite dimensional unitary transformations. In other words, if you have a compact group, each group element can be represented by a matrix that is a finite dimension and unitary. So in other words, what you have is d dagger of g, d of g equals the identity, okay? And so that's if the group is compact. On the other hand, some groups are not compact, such as the translations, the boosts, the Lorentz transformations, the Poincare transformations, the general coordinate transformations. These are non-compact groups, and they don't possess finite dimensional unitary transformations. They possess infinite dimensional unitary transformations and finite dimensional non-unitary transformations, but not finite dimensional unitary transformations. By the way, there are two terms that sometimes show up in physics and are ubiquitous in mathematics. A set is closed if the limit of every convergent sequence of points lies in the set. And a set is open if each of its elements lies in a neighborhood that lies in the set. And the examples are in one dimension, if A and B are two numbers, A less than B, then the set of points X between A and B, or the open interval, is open, and the closed interval is closed. And the reason here is that you can have a set of points in the closed interval that approaches B and that approaches A, and A and B are in the set. Whereas here, you can have a set of X's that approach B, but B isn't in the set because it's an open interval. All right, one thing that's also important here is that every n by n matrix S that is non-singular, that is to say has a non-zero determinant, will map every representation of a group into an equivalent representation. So in other words, for every element G in the group, you have a matrix that represents it, D of G, and now if you multiply that matrix by S inverse on the left and S on the right, you get a new matrix, and this is a new matrix of a different representation. But that representation is related to the original representation by a similarity transformation. And so it's said to be an equivalent representation. And we really don't distinguish much between the two. A proper subspace of a vector space is a subspace of lower dimension, but not zero dimension. And a proper subspace is invariant under the action of a representation if D of G maps every vector in the subspace into another vector in the subspace. And the way that can happen is that if D of G is, or at least if you can take D of G, suppose you can take a representation and make a similarity transformation so that it's block diagonal. Well, then it is reducible to I think this is called a direct sum of representations D1, D2, and so forth. Okay, well, I'm putting a lot of stuff before you very, very rapidly. You can, of course, and are encouraged to read the stuff in the book at your leisure. It will do you no harm. Representations acting in Hilbert space. Well, in quantum mechanics, a symmetry transformation is a map between states, psi goes to psi prime, phi goes to phi prime, such that the inner product of the states that is has an absolute value that's the same. So in other words, the probability of psi being phi is the same as the probability of psi prime being phi prime. So, and one of the important theorems that was proved by Wigner and improved by Weinberg is that the action of a group of symmetry transformations on the Hilbert space of a quantum theory can be represented either by operators U of G that are linear and unitary. Linear, linear means that U of A state 1 plus B state 2 is A U of state U on state 1 plus B U on state 2. That's linear and unitary, or by ones that are anti-linear and anti-unitary. as far as I know, time reversal is the only case where the representation is antilinear and anti-unitary. I frankly find antilinear, anti-unitary transformations to be spooky. And of course, time reversal is also spooky. It somehow seems to be less spooky, but it certainly is spooky. And of course, sort of things you could do with time reversal if you had a time machine would be quite fantastic. And I'm going to avoid that tempting tangent. Let me go on, though, to something that I'm skipping a lot of stuff here. Well, there's morphisms. I maybe should have said something. An isomorphism is a one-to-one map between groups that respects the multiplication law. And a similarity transformation, for example, relates to equivalent representations. It's an isomorphism. An automorphism is an isomorphism between the group and itself. And well, all right, that's enough. I'm going to, well, maybe I should say what Schur's lemma is. I'm not going to prove it. If D1 and D2 are inequivalent, irreducible representations of a group, and if D1 of G A is equal to A D2 of G for some matrix A, and all G in the group, then the matrix A must vanish. So that's part one. Part two, if you have a finite dimensional irreducible representation D of G of a group G, and we have D of GA is equal to A D of G for some matrix A and for all G in G, then A is a multiple of the identity. So so that's important, but I don't think we need to dwell on it now. I want to get on to something that is related to general relativity. By the way, this thing on Lie algebra, you could be, I'd encourage you to read that. If I get through what I want to do now. All right, so I want to say some things about Yang-Mills theory and gauge theory, and the standard model is basically one big, huge example of Yang-Mills theory or of nonabelian gauge theory. The basic idea is that the action of Yang-Mills theory is unchanged when a space-time dependent unitary matrix, and here these thetas are just real parameters that depend upon space-time. These T's are matrices that are Hermitian, and so this is a unitary matrix. And this unitary matrix will map a vector psi of matter fields into another vector of matter fields. And so the idea here is that psi of x here is psi 1 of x, psi 2 of x, or psi n of x. You know, you can have n of them. An example here would be L of x, and you might think of that as the neutrino field and the electron field. I'm talking quantum fields here, quantum field theory. Now, if you have some vector psi and u psi, and then u dagger psi dagger prime would be psi dagger prime would be psi dagger u dagger. If here I'm saying that psi prime is u psi, then psi dagger prime is psi dagger u dagger, and psi dagger psi prime would then be psi dagger u dagger u psi, and u dagger u would be the identity, so this would be psi dagger psi. So it's very easy to conceive of a theory that is invariant under unitary matrices, but what was the stumbling block is how do you get derivative terms to be invariant? And of course, this is a problem that was solved in a more complicated and significant context by various mathematicians, Riemann, and it's physical. It was brought into physics by Einstein in general relativity. But it had already been solved in the 19th century for the case of abelian groups, although it wasn't quite recognized as being that. And what Yang and Mills did was they introduced a connection, which was basically a linear combination of the matrices TA, the same TA that are here. These things are called generators of the Lie algebra of the gauge group that we're talking about. And these matrices then multiplied by gauge fields, which are connections, and then an overall I. Why is there an overall I? Well, it's this obsession we have in physics with only dealing with real observables. And so if we have an observable that's actually imaginary, we stick in an I and factor out the real part, call that the observable. Anyway, what Yang and Mills did was they said, we're going to replace this derivative with the derivative plus a connection. We're going to call that the covariant derivative. I don't know who introduced the term covariant, but it's an appropriate term because it's like the covariant derivatives in general relativity. And they then required that the covariant derivative, the transformed covariant derivative, and that's why there's a prime here, times the transformed field be equal to U, the transformation acting on the covariant derivative. Okay, so this is the covariant derivative after the gauge transformation. And so what is this? Well, the derivative here is acting on U as well as psi, and that's what causes the problem. And so you have di on U plus U di on psi, and then you have A prime U psi. So that's what you've got. And then what Yang and Mills did was they realized that for a general Lie group, you could solve this equation for A prime. And indeed, A prime I then is given by, if you just, all right, let me just add an equation here. So what we've got here is diu psi plus u di psi. So I'm writing this out. Plus AI prime U psi has to equal this right-hand side, which is U di psi plus U AI psi. Okay, so there are going to be some cancellations here. So let's do the cancellations in green. Oh, damn, I wanted to make this green. Cancellations in green, so these two things cancel. And now we can factor out psi, And if we factor out psi, then what we get is diu plus ai prime u is equal to u ai, factoring out the psi. And so this tells us then that ai prime u is uai minus diu. And now U is just a unitary matrix, so we multiply by its adjoint or its inverse, and we get a formula for AI prime. And it's equal to U AI, U inverse or U adjoint, minus DIU, U inverse. Or, well, let me leave it that way. I think it's better to leave it that way. So this is the transformation law then of a connection or of a Yang-Mills field. Here, I'm taking advantage of the unitarity of the transformation U, so U inverse is U adjoint, and that's the transformation. Then what you can see is that with the magic of anti-symmetry, if you take the Faraday tensor as being the commutator of two covariant derivatives, then you get diak minus dkai plus the commutator of the matrices. These guys here, you see, are matrices. This thing is a matrix. This is a matrix. And of course, these are also matrices. So these are all matrices. And this transforms homogeneously. That is to say, if you put in the primes here, then and you write what A prime is, what happens is all of the inhomogeneous terms cancel, and you just get that the primed field strength is U times the unprimed field strength times U inverse or U adjoint. So that's basically what Yang-Mills's trick was, and you see it's very similar to what I started today's lecture with, namely that the affine connection here is what one adds to the ordinary covariant derivative to make the derivative covariant. So the covariant derivative transforms like a tensor, but the thing that you add, the connection, isn't a tensor. Because it transforms inhomogeneously. And the reason it transforms inhomogeneously is it has to cancel out the inhomogeneous term that occurs when this derivative here hits the U of X. And so that was this term. What was that? I don't, oh God. I know these touch sensitive Apple devices, I don't know where I am with them. I touch one of them and the world ends. So this, the interesting thing about, one of the interesting things about all of this is that the gravitational interactions, of course, are entirely due to these gammas. And because the curvature tensor and so forth is, or the curvature of space-time, in other words, is related to derivatives and products of these connections. And why do we have those connections? Well, we have those connections so that we can make everything a tensor. In Yang-Mills theory, we want derivatives to transform in a nice way. In other words, we want the derivative to transform like covariant derivative. In other words, the covariant derivative on the transformed field should be the transformation acting on the covariant derivative, so that the covariant derivative it transforms like the fields. And in the case of general relativity, what we want is that we introduce this connection so that these various things are tensors and transform like vectors or like derivatives, or products of vectors, products of derivatives. And so in order, and what one has, when one has made everything transform covariantly or contravariantly, like tensors in the case of relativity, one has as a result of this, one has gravitational interactions, which are due to the curvature of space-time. And then in the case of Yang-Mills theory, or the standard model, all of the interactions are required by symmetry. That is to say, they're all due to these extra terms that are introduced. That is to say, this gauge field that's introduced in order to make a derivative covariant, these are the things that transmit forces between quarks, or between leptons, or from leptons to quarks, and so forth. So what's interesting here then is that all of the interactions that we know of in physics are due to connections which are introduced in order to have local symmetry. And so symmetry is playing an enormous role in the physics. Well, I'm over time. I'm going to stop now. Let me check the chat thing if I can find it. I can't even find it now. I don't know where it's gone. Well, I don't, since there's the chat, it's still blank. So I'm going to end here. Wish you all a good night. The class tomorrow is at 5, and I'll do something probably low-hanging fruit. And, instead of an exam, I'm going to give a lecture at the time of the exam. And I forget when the exam is, but I'll tell you tomorrow when the exam is, and I'll give a lecture during the exam. And what I'm trying to do in these last lectures is pick some of the low-hanging fruit and give it to you, so that you learn a lot of the easy things in the chapters that I haven't had time to cover. We used to have a second course called 467, but we don't teach it anymore. So I'm going to end